Okay, this is a tree map of Unit 10, which is about infinite series. On a very broad level, Unit 10 is about two main topics. It's about examining an infinite series that is a sum of a bunch of numbers. And along with that, we looked at how to determine whether that kind of sum converges or whether it diverges. The other big part of Chapter 10 is examining power series, which are a lot like infinite series. The difference between power series and infinite series is that power series look more like an infinite polynomial. So there'd be a coefficient, but then also an x to the n. So broadly, that's what Unit 10 is. It has two halves that are kind of logically follow from each other. We start with infinite series with just numbers in them, and then we introduce the idea of infinite series with x's in them. When we just have x's in our infinite series, we focused on finding the convergence of those series. That the idea that we're adding infinitely many terms together and sometimes we come up with a number is a little bit disturbing. It seems like we shouldn't come up with a number if we're adding up infinitely many terms, but sometimes we do. If adding up infinitely many terms results in a number, then we say that our series converges. If it doesn't result in a number, then we say our series diverges. Partial sums would be one way to determine what our series adds up to, and that is one method. But it's often too tedious and time-consuming to actually use that method, so we have a bunch of tests. The first test is not a convergence test, it's a divergence test, and it's called the nth term test. On your salmon-colored sheet, it's called the divergence test because it is a test for divergence. If you take the limit as n goes to infinity of just the terms, and they're not equal to 0, then your series diverges. What that means is if I'm adding up infinitely many terms, the only way that it could possibly converge is if my terms are getting so small that they approach 0. Otherwise, the series diverges. The problem with the nth term test is that it does not show convergence. So after you try the nth term test, you're going to have to look at another test to show actual divergence or convergence. There are some special kinds of series that are useful. One special kind of series that's useful is a geometric series. If your series happens to be geometric, then it will look like it will have some starting term, and then it will have a common multiplier. And this kind of series converges if the absolute value of r is less than 1. If the absolute value of r is greater than or equal to 1, then it diverges. The nice thing about geometric series is that we can not only tell whether our series converges or diverges, we can tell what it converges to. So the sum would be a over 1 minus r for a geometric series, as long as the series converges. Another special kind of series that is a useful one to know about is a p-series. A p-series is one that looks like 1 over n to the power of p. That series converges if p is greater than 1, because our terms are getting small fast enough for that to converge. And if p is less than or equal to 1, that series diverges. those two series are really easy to identify and easy to identify convergence or divergence. Unfortunately, not most series are not straight up geometric or p-series. In the case that it's not a straight up geometric or p-series, you might want to do a comparison to a p-series or a geometric series. So there are two comparison tests. There's direct comparison. And for direct comparison, you have to compare your series, the one you're interested in, to another series. And if all of your term, and let's say we're going to compare to a series that converges. So one option is we're going to compare our series to a series that converges. And what we do is we say, okay, well, if every single term of our series is less than or equal to this converging series, then our series converges. But we might want to prove divergence with the comparison test, and it actually works. So we can compare our series to a series that diverges. And in that case, what we have to do is show that every single term of our series is larger than the diverging series. So if we can show that, then we have divergence. But direct comparison is really helpful for something like 1 over n squared plus n. We could compare that to 1 over n. So if this is my series, I could compare to 1 over n. And I know, actually it's 1 over n squared. And I know that every single term is larger than 1 over n squared. And so I can say with confidence that direct comparison works. But if this were just something like n squared minus n, then direct comparison doesn't work for every single term. So we can't use direct comparison in that situation. What we do instead is we say, well, those are basically the same series, so we do a limit comparison. And what limit comparison does is it lets us just compare kind of the behavior of our function, and if it approximates another function, then we have either divergence or convergence. I think limit comparison is a little bit easier than direct comparison because we don't have to go through that additional step of showing that our series is bigger or smaller than one that converges or diverges. What we do instead is we say, okay, we know the behavior of B sub n. It might be that it converges, it might be that it diverges, but what we do is we say, is my function essentially the same as that function, or is it mostly the same? So I'm just going to make a ratio out of my series and the one that I know about. If this is a number, a positive number, so not 0 and not infinity, if that limit is a positive number, then A and B do the same thing. The ratio of those terms as n goes out to infinity is just a multiple, like if A is just like 2 times bigger than B, then we get a positive number and we say, okay, it converges or diverges. So these two converge or diverge together. So we have to know the behavior of B sub n. But once we do that limit, and A sub n will do the same thing as B sub n. Important note here, it doesn't matter which one you put on top, because if you get a positive number that's not 0 or infinity, then if you do it the other way, you'll just get the reciprocal. So, and then maybe you look at your series and it looks a lot like something that you could integrate. And that would be the integral test. And when I say you could integrate, I mean you can find an antiderivative. So if I have a series that looks like a function that I know, and I know that I could integrate it, then I can do the integral test. And what we know from the integral test is that these two converge or diverge together. So if I do the integral and it diverges, then so does the series. And if I do the integral and it converges, then so does the series. But there aren't a lot of functions that have nice, easy antiderivatives. So the integral test is probably not the biggest one that you'll use. What you'll probably wind up using a lot, though, is you'll probably use the alternating series test. Again, it's in a very specific situation. You can use the alternating series test whenever your signs alternate, like actually negative, positive, not like a mix of negatives and positives, but it has to be every other one. If your signs alternate, then you can just look at how big your terms are getting. If the terms are always getting smaller, so each future term is smaller than the one before it, and if your terms are approaching 0, then that's enough to show convergence for an alternating series. It's not enough to show convergence if the signs don't alternate. It's also, if one of these is false, then your series diverges. But again, not most series are not alternating. So if you don't have an alternating series and you can't do integral tests and you can't do p-series and you can't find a comparison, then my favorite test is the ratio test. The ratio test works because you can compare your series to itself. You don't have to come up with another series. So you do the limit as n approaches infinity of just what's going on with my terms. How slowly are they approaching, what's the ratio between my terms? And I look at that ratio and I get a number. If that number is greater than 0, I lied. If that number is greater than 1, then my series diverges. Actually, if that number is greater than, oh, yeah, that's it. And if that number is less than 1, then my series converges. The problem with the ratio test, and the thing that breaks my heart about the ratio test, is that if that ratio is 1, then we don't know what happens. We have to do another test. It's inconclusive if the ratio is 1. Okay. So that's how we started the chapter. We started the chapter with all of these convergence tests. We were looking to see whether our series converged. For the second half of the chapter, we introduced the idea of having a series with an x in it. And that will be the second half of this tree map.